Search, as a discipline, has been around for decades. We live in this information age where data has become the new gold. And probably the most important underlying idea is how do we access and search through all this information? As technology evolves, so does the search techniques. Lexical search has been the predominant way in which we implement search engines for many years. But now there's a new way of searching that has strongly emerged and is reshaping the way we conceive and we implement search scenarios. One that is powered by ML and is known as vector search. So in today's session, we'll be covering both the basics of lexical search and vector search, what are their differences and their strengths. Then we'll go into vector search a bit more in detail, what's happening under the hood. And then we'll see how we can implement vector search scenarios by leveraging the capabilities of Amazon OpenSearch Service. Then I'll leave the stage to welcome my colleague Amir that will guide you through their use case at Lyst. And then we'll end up with a summary with the key points I want you all to take home. Now let's jump right into the search methods. We have on the left side of the screen lexical search. Lexical search is also known as exact match search. It's known as exact match search because basically what is going to happen is that your query is going to be broken down into individual words or tokens, and those words are going to be looked and searched across all the documents that you have stored in your database. If those words are found in the documents, then those are going to be retrieved back at you with some search relevance results. As you can imagine, you really need to take a close look to choose the words because depending on the words you use, you're going to get better or worse results. Then, on the right part of the screen, we have vector search. Vector search is a more advanced kind of search in the sense that it's able to understand the semantic meaning of your query. As opposed to exact match search, what it's going to do is going to find similar results. And that's why it's also known as similarity search. Thus, three words for the same concept: vector search, similarity search, or semantic search that represent the same idea. You're going to see it much clearer when we see an example. So let's imagine a first scenario in which you have a user that is looking for a new piece of furniture for their living room. In this first scenario, we have it very clear that they want an 8-foot blue sofa, and that's what they're looking for. In this scenario, when you know exactly what you're looking for, it's a great example for lexical search. You could go into Amazon.com, type 8-foot blue sofa, and get some results back. These lexical search results are probably going to be very relevant. Why? Because probably all these words that you chose are going to be present in some of the fields that describe a product. Maybe the 8-foot will be in the size description, maybe the blue will be in the color metadata, or the sofa in the product category. Now let's imagine a second scenario in which, again, we want to buy a piece of furniture for our living room, but we have no idea what we're looking for. So, we just want a cozy place to sit by the fire and maybe watch some football game on Sunday evening. So in this case of a scenario, lexical search won't work for us. We need a kind of search that understands the semantic understanding behind this search. And thus, we need vector search. But where do we start? There's going to be two main steps. Let's oversimplify here the process. The first one is to get the numerical representation out of the text. So here we're going to go from the realm of text and words into the realm of numbers and vectors. Vectors can have many dimensions, usually hundreds or sometimes thousands of dimensions. And you can think of a dimension as a descriptor for a query. Therefore, you can see that encoding the information into a vector gives us a much more richer representation of the query that we're looking for. Now, these vectors are also known as vector embeddings or just embeddings, in case you see it around. The second step is to find the similar vectors in our database. Here we can represent them, just oversimplifying it in 2 dimensions, and we can represent our query, find me a cozy place to sit by the fire, in the green vector, and look for similar vectors. How do we measure similar vectors is another topic that we won't go into much detail today. But basically here you can see that we have vectors that are close by that represent things like a couch or a chair. Basically, it got the understanding, the semantic understanding of what a cozy place to sit by the fire is, and found products that are similar and represent that full idea. Now, something that is also critical and sometimes forgotten is to measure the search relevance after we implement a search engine. We cannot just expect the search to work. We really need to measure, and this needs to be an iterative process that we improve all over and over. But probably you may think, okay, this is very subjective, right? Maybe the search results that are relevant for me maybe are not as relevant for you. Okay, this is known, and this is a field of study, and that's why measuring search relevance is complicated. But most of the metrics agree that there are two parameters that need to be taken care for measuring search relevance. The first one is how many of the search results that you get back from a specific query are actually relevant. So if you get 10 search results, how many of those 10 are somehow relevant? And the second part is the ordering of the results. Are we returning the first result, and is it the most relevant? Is the second result more relevant than the third? And so on and so on. And those two parameters are the base of all the metrics that are surrounding search relevance. The great thing that happens when we have a measurement of search relevance is that we can compare different implementations. I wanted to bring this example up. As you can see here, what happens when we compare search relevance between just applying lexical search, that is the second column, against a combination of lexical and vector search on the third column. Here you can see that on average you can achieve 15% higher relevance, and I really encourage you to go ahead and take a look to the QR code if you're interested in learning more about this study. So far we've talked about vector search in the realm of text, but I want you to think beyond that, because actually vector search can be applied to any kind of data type. So, for example, Amazon Music applies vector search to songs. If you are able to transform songs into vectors, then you can influence and recommend similar songs that the user has listened based on the past history. Another important key point I want you to think is about the scale. This not only applies to vectors with millions of vectors, but you can also go into the billions of vectors. As is the case with Amazon.com, that is able to search across more than 60 billion of vectors, in which the description of the product is transformed into a vector and allows you them to do intellectual property infringement detection, so you can detect frauds and remove them before they do any harm to the end user. Now, the last step in our journey to implement vector search, it was what is the technology that we're going to use to build this kind of search engines? And the answer is OpenSearch. OpenSearch is a community-driven Apache 2.0 search and analytics suite that is going to allow you to ingest, search, and analyze search results. Basically, you can run OpenSearch by using Amazon OpenSearch Service, that is the fully managed AWS service that is going to allow you to run these OpenSearch clusters without needing to worry about the underlying infrastructure and maintenance of it. With Amazon OpenSearch Service, you're going to be able to implement both lexical and vector search. You're going to be able to do analytics on top of those results via the use of OpenSearch dashboards. You're going to get a great integration with other AWS services, like, for example, the use of Amazon Bedrock to transform the text into these vector embeddings. It's going to allow you to create cost-effective strategies, like integrating Amazon S3 in order to reduce storage costs. And finally, it comes in two main flavors. You can use the serverless deployment option with vector collections that is going to follow the best practices, and you just go and start straight away to implement your vector search implementations. Or you can opt for a managed deployment in which you can have a finer grain control of the underlying cluster, like the number of nodes or the instance families that you're going to use to run those nodes. OpenSearch has this kind of structure called the plugin that allows you to expand the extra functionality that comes inside OpenSearch and their core APIs. Here you can see the 4 plugins that are related to machine learning scenarios, and you can see on the top part the 2 of them that are related to vector search. This is the KNN plugin, and this is the neural plugin. For the search and completion, we also have other ML plugins, like the learning to rank plugin, that is going to allow you to re-rank results based on the past user history. And you also have the ML Commons that allows you to bring other machine learning algorithms into the realm of OpenSearch in order to do other activities like recommendations or predictive search. Now, let's go a bit more into detail on the 2 plugins related to vector search. The first one, and the core of all of it, is the KNN plugin that stands for Key Nearest Neighbors. This is the plugin that has been along for the longer time, since 2020, so now it's more than 4 years old. We've been evolving it and adding new capabilities based on our customers' feedback. And you can have here the transformation and, the search of the vectors and finding the similar vectors. You can use different libraries, like the Lucene library, the FAISS library, or the NMSLib library. That are different implementations of the KNN algorithm. And you can also use different alternations or variables of the KNN search, which are the approximate KNN, which works great for use cases where you have billions of vectors. You have exact KNN when you need maximum search relevance, or you can even do further customizations with painless extensions. The second one is the neural search plugin that is going to answer to the question of how do I transform the text into the vector? Basically, the first step of the vector search that we touched before. With the neural search plugin, you can do that, and it will be done automatically, and you won't have to deal with this initial step. Basically, you're going to send the text to OpenSearch, and OpenSearch is going to handle the part of transforming the text into vector and storing it or doing the search against the other vectors. Of course, for every transformation from text to vector, you're going to need a machine learning model. And you can bring the machine learning model needed to do this transformation in 3 different ways. You can use one of the pre-trained models available inside OpenSearch natively. You can bring your own ML model into the OpenSearch cluster, or you can connect to external services in order to do this transformation. This third option is actually a great way to decouple your architecture and have more flexibility on how you calculate the vector embeddings. This third option is done with the so-called ML connectors. The ML connectors allow you to implement easily this connection to external providers, and you will be able to use services like Amazon Bedrock, Amazon SageMaker, or OpenAI to create the vector embeddings. Then, once you have the vector embeddings, they will be stored in OpenSearch, and you will also be able to leverage all the infrastructure and all the access controls that are available natively in OpenSearch. Now, I want to welcome to the stage to Amir, that he will go through their use cases building vector database solutions at Lyst. Thank you.
Cool. Thank you, Francisco. Thank you, Francisco. That's a great introduction to OpenSearch and its semantic search capabilities. So, my name's Amir. This is me. My background, I trained in aeronautical engineering, worked in finance for a bit, building risk and pricing models, ran my own startup for a while, and then moved into Lyst, where I've been running their marketing engineering and then building models for predictive bidding and attribution algos, and for the last few years, managing a crack data science and machine learning teams to build search and recommendations results. So today, I'm going to tell you about how we at Lyst, as a small startup, now probably scale up, have been leveraging OpenSearch, vector search, to deliver these semantic search and personalization features and products for our end users. And really, it's allowed us as a small crack team probably 70 engineers in the company, 10 data scientists-ish, to punch above our weight in delivering these features. Before I get there, I'll tell you a bit about Lyst. Not everybody's heard of it. So I'll start with e-commerce. I would like you to, could you raise your hands if you have bought something online in the last year? Great, as expected, give or take 100%, maybe 95%. Now, could you please raise your hands if you've bought an item of fashion online in the last year? So clothing or shoes, pretty good. Looks like maybe 50%. I think we have a fairly tech-savvy audience here. The wider stat in the market is about 20% of people buy fashion online. When Lyst started, that was low single digits. So Lyst's aim is really to make online fashion purchasing easier, smoother, better, a more satisfying experience. So I'll just show you the Lyst product as an example. Here's our key pages. This is the core of our site. This is what we have. This is standard amongst other e-commerce platforms, but ours is fashion. This is a product page. We have all the detail about a product, the prices, sizes, colors, etc., where you can buy it from. And further down here, we have all the related products. So that's one of our key pages. The other one is what we call a feeds page. This is a collection of products that all have some unifying theme. In this case, we can see bags for women as a unifying theme. You can imagine there are many more. Hopefully, it should come as no surprise whatsoever that this collection of products is powered by OpenSearch. So I'm going to talk through some of the history of OpenSearch at Lyst. How did we get here? How do we use OpenSearch? More the lexical search bits, the non-semantic search parts. That's sort of the baseline. And then we'll talk about how we've been using OpenSearch as a vector database and what features has that allowed us to build that we wouldn't otherwise have been able to build. This is the blurb about Lyst. I think the key thing I'll draw your attention to here is we have 8.5 million in-stock products on the website, fashion products that you can search. Unlike some other larger retail companies I could care to mention, we don't have a warehouse, we don't hold inventory, we don't have these in stock. The way we work is we partner up with 1,000+ other fashion retailers to get all their products onto our website. And then our website serves as a central place where customers can then find the thing that is right for them, the right price, and the right color, and the right size. So, great concept, right? Couple of problems. First problem is sourcing data from 1,000 retailers. As you can imagine, it's not standardized. There's a lot of work we do, that's maybe half the company, to ingesting all that data, categorizing it, understanding colors, styles, putting it into a single uniform format. Of course, there's a whole bunch of machine learning models and development that has gone into that. And then once the data is into Lyst in a standardized, uniform way, we have the second problem, which is how do we help our customers find the product that's right for them out of these 8.5 million? That's where OpenSearch and semantic search comes in. So a couple more stats. I think the key ones here are the rate of product updates. We're getting updates from our retailers, our partners, all the time. We're getting 15,000 product updates every minute. We're getting 10,000 new products every hour, products that have never been seen before on our site. So why are these relevant? The first one is the new products. Fashion, as you can imagine, we're in the business of fashion. People want what's trendy, what's latest, what's new. We don't want to lag behind. If something's new, if Kim Kardashian has worn something, somebody else has been on the Paris Fashion Week, people want to come and find it the moment it's available. We can't delay having that product available. So we need a system that allows these products to be available as soon as possible, really. The same with the product updates. Products are going in and out of stock. Sizes sell out, they come back, they go on sale. It's continually changing. If a customer finds a perfect product for them in the size they want, at the price they want, and then they try and buy it and realize it's actually out of stock or it's a different price, they're not very happy. So we are trying to keep up with this data rate. That's probably the most challenging part of this. And here to summarize that as a diagram for what, as I say, half the company does, neatly encapsulated in that middle blob of moderation. Not to diminish their work, it's a huge amount that goes into it, but that's a subject for another day. That's getting all the data in from our retailers. Spot the deliberate mistake. We have more than 3 retailers, even more than 2 number 3s. Once the data is in, this data then goes off the right-hand side into OpenSearch. So let's talk about how do we use OpenSearch. What's the basic part of it? So those feed pages I mentioned earlier, that is the bread and butter use case for OpenSearch. We have been doing this for a long time. As a shopping site, we are generating various hundreds of thousands of different collections of products that are available. That's essential functionality. We had bags for women, we can have Gucci dresses, we have red stiletto shoes, and so on. If you can imagine it, we would like to have that page. And then with these pages, they're predefined ones, and then there are also pages that, the search results pages where people are searching for something. These are also other collections of products. People can filter on these and narrow it down to the products they're interested in. All of that maps pretty much one-to-one with OpenSearch and the filters that are available, and we're doing a lot to map. It maps one-to-one, but there is still a mapping process to convert what a user wants into a query that can be run on OpenSearch. Now, how do we get here? So it's a little bit of the history. We started off implementing our self-managed Elasticsearch cluster probably 10 plus years ago. This was wired straight into our website code. This is back when we were a really small, scrappy startup where things have to be delivered fast and you've got to make it work or else we're not going to get to the next year. Of course, after that, we've grown our customers, grown the market. We're able to add some sense into this. We're able to develop an API layer within our website to separate out how do we talk to Elasticsearch. Of course, as the trends in the market, we've then moved these key business areas into microservices. We've moved the Elasticsearch wrapper into a separate service, which the main website can call, which gives us that confidence of a degree of separation, helps us to understand how we're calling Elasticsearch better, how to optimize that, how to improve those queries to give the results we want, and of course all the other benefits we get from that being a microservice. As you can see, the next steps are from calling our own self-managed Elasticsearch cluster. Amazon, at about this time, offered a managed service. Of course, we planned and made that switch in 2017. And then most recently, the large change has been the upgrade from Elasticsearch to OpenSearch to give us the latest features that are available. So one more about what we do with OpenSearch before we get to the semantic search. So here's some ideas of, if you use OpenSearch, what are the things you're trying to do to improve that experience? It's not a matter of just implement OpenSearch and leave it. We can always be making improvements. So the first one I'll talk about is ranking, really. We've mentioned learning to rank models, which will work for a subset or a re-ranker. If we have 8.5 million products, we need an initial way to find the most relevant products for a user. So the way we've implemented that is we can generate some sort of global scores, which says how good a product is. And one example of an improvement there is we've gone from a single global score to multiple different scores, which can be combined at runtime using script scoring as a feature that's more recently available. And we can dynamically adjust that script to decide for any given user or query, how should we rank their product in the optimal way to get the best, most relevant collection of results. So again, basic ranking there. The next kind of thing we can do, text search. The lexical search that Francisco mentioned, again, it is not a fire and forget. There are many parameters, there are ways of tuning it, trying to decide which fields should we be searching over, what weights, how do we improve that, how do we get better, more relevant results. There's still a place for this, even in a semantic search world. And we saw the results earlier was text search versus a combined text and semantic search. So we still want this to be good. We still want to work on improving it. We can still run tests and drive that to be better. Last one I'll mention, so we run this outside OpenSearch, re-ranking. When we have our narrowed down list of products, we can then take customer attributes into account. What do we know about that customer at that time? How can we add more intelligence about fashion, about which sizes are relevant to that customer, which sizes are popular, and do further re-ranking to deliver better results. So that is OpenSearch without getting to vector search, status quo. So now we're going to talk about how do we use the vector search capabilities to really take us to the next level of semantic search, personalization, and the more advanced things that we'd like to do. So this all hinges, in our case, so far, on the vector database. And what's the key thing? We need this product embedding to be able to use a vector database. We need a way to map that product, that fashion item, whatever it is, into this sequence of numbers, which can go into the vector database, which we can then do our similarity searches on. Now, of course, that's not so simple. There are many ways to map a product into a vector. We have tried various ways over the years. We have tried collaborative filtering approaches where if two products are viewed by a user in the same session, we will train a model to generate embeddings for those products that are close together in vector space. That's one way. We can take the text of the product description, create an embedding for that, and put it in. It's another way. We can combine these. The one we have found most success with at the moment is purely an image-based embedding, and where we can take the image itself, generate an embedding from that, put that as our vector search. The advantage over using static features of products, especially when we have a large database, is that we only need to calculate this once. If it was performance-based embeddings or collaborative filter-based embeddings, we'd have to re-update those as we get new data in, new interactions. The current approach means we're only indexing new products when we see them for the first time. We use other Amazon features, such as SageMaker, batch transforms, to efficiently and at a very sensible cost, do small batches to keep us up to date within pretty much minutes, to make sure all our new products are indexed into the vector search database and available to query. So having got our embeddings into our vector database, what can we do with that? And this is where the opportunities open up, really. I'll talk you through three. There are more that we have at Lyst, probably three by order in which we've done them. First one I'll talk about is image semantic search. Now, I've skipped a bit here. Users, when they want to search for products, they're not going to give us the vector itself. They're going to give us something else. And we need to take that something else and transform it into a vector. So in this case, the user can give us an image to start with. And then we can look at how do we transform that into a vector. We've tested transform the whole image. When it's a complex image with multiple products in it, that doesn't work so well. So in this case, we need to do some object detection and to actually get this tested, because this is a new product, a new feature. We used a third-party service to allow us to do that, and then to be able to search the products and find the relevant products in the Lyst catalog that were in the image the user uploaded. So the next use case, we've had images come in. This one's more text. Users can, of course, type in a text query. We can convert that into an embedding in the same space as the image embedding. Now, to do that, we need to have trained a model that has a particular characteristic that's known as a multimodal model. We can train it with pairs of text and images, and by constructing that model in the right way, we ensure that both those embeddings appear in the same space. So in the 8-foot blue sofa case earlier, we would train it so the embedding for that text has a very similar, it's very close to the embedding for a picture of an 8-foot blue sofa. That allows us to do things like text semantic search and allows us to get results by meaning. There's another use case for this. We can take user text queries. Another feature we have live is generating those text queries ourselves. I mentioned we categorize our products. If you can imagine, we get hundreds of thousands of dresses in. We try and categorize them. That's actually quite difficult to categorize them to a really fine-grained, precise level of detail. And it turns out it's actually unnecessary. We can let the semantic search feature find all the dresses of the right category at runtime when we need to. So we might have on site, pre-semantic search, things like cocktail dresses or maxi dresses, but not too many other categories. What we can now do is generate pages for A-line dresses, bodycon dresses, all these very specific things. And the key thing there is that these subcategories are not going to be in the text. If somebody just did a text search for A-line dress, that wouldn't get you very many results. If you do a semantic search for the same term, you now get hundreds of results, which are visually, that's what the customer is looking for, allows customers to see the things that they actually want in the way that they are searching for it. And by pre-generating these pages, they can find them straight from your favorite search engine and hopefully find the products that they're looking for. So that's been rolled out. We're seeing success in that. We're going to scale it up. The last interesting thing I'm going to mention, not the last interesting thing by far, there are more, is the personalization use case. Now, in some cases, some companies, customers have a login. We know a lot about the customer. We know lots of features. We can segment the customers and personalize based on that. That's not how Lyst works. Lyst is open. You don't need to register. You can come and use the site as an anonymous browser. We still want to deliver a better experience for that use case, in addition to our signed-up members, of course. So here, the main source of data is the interactions, the products that that customer chooses to look at. No two customers have the same sequence of products that they've looked at. That's a very rich source of data. And we can look at which products have they seen so far in their session, and from that, try and extract their style. What's their taste? What's that indefinable, indescribable thing that describes what they're actually interested in, and process the embeddings for those products to then generate a new embedding that is trying to capture their style or their taste. And we will use this new embedding when we are generating results for them to hopefully nudge those results in the direction that gives them the products they're looking for, and a bit more of a satisfying experience and something they actually want to see rather than having to scroll through pages of results and not finding it. Of course, in practice, you don't only show personalized results. They will still be interested in what Kim Kardashian was wearing, other popular results. We'll just blend them. There's a whole science of search results and diversification that goes into this. But the personalization element is a key new extra lever that we can offer. It's a brief, put in one or two technical diagrams, not very technical, vastly oversimplified, of course, but how the systems work. On the left, we have our product data, new products coming in, going through SageMaker, generating those embeddings, going to OpenSearch. And on the right, we have the Lyst product. People are using it, browsing it. We generate an analytics stream of which products have they interacted with. in real time. Normally, this would go to a warehouse with some batch things. We can't query it from the warehouse. But by using Kinesis and the other streaming data streams, we can hook into that, pick up these interactions in real time, feed them back into the OpenSearch query, keep this user embedding up to date, and deliver personalized results from after your first interaction with minimal delay. So why are we using OpenSearch for this? So Lyst, as a company, we've always tried to focus on our data science, machine learning model efforts. We have experience with other k-nearest neighbors libraries. In fact, we have an open source KNN library that we've developed that's still used by other people that has particular use cases. The hard bit has been, the stumbling block has been that most of these other services are standalone KNN vector databases. They don't combine with all the other filtering and the pages and the results we want. Or if they do, you have to put all that data in as well, which creates an extra bunch of engineering, extra workload that turns out for us is unnecessary. Since we had all our basic data and attributes in OpenSearch, and since they've offered the KNN plugin, the vector search database, this is by far the cheapest and easiest step up to providing that combined semantic search with filtering and all the other ranking and all the other work we've done over many years to give good results, and just improve it rather than trying to start again from scratch, which as a small team, it would have been prohibitive. So how does this work in production? Of course, the first time we rolled this out, it's fair to say it didn't go smoothly. We learned. We had a lot of learning to do. It turns out the vector database, it needs to be kept entirely in memory. It can't go to disk if you want performance. We learned that. We learned about how do you even monitor that. So we picked up all the new metrics and alerting and logging that we needed. We learned about how do you tune that vector index. There are many parameters in the construction. Each will be different for different people's use cases. And of course, choosing which algorithm works best for us. As mentioned, we're able to A/B test and figure out for us, for the rate of updates to the index, for the size of the index, for the latency we want, what's the best tune for that. And together with that, it's also figuring out what cluster, what size do we use, how do we get the experience at the end of it that works for everyone. So I can report that our first experiments using personalization have delivered strong commercial results for us. We were able to improve conversion rates by 16% in this particular test. So of course, we've scaled that out. We are rolling this out further. And again, to summarize really, this is all possible because we can focus on the bits that we're good at, which is understanding fashion, building those machine learning models to understand fashion, and we can leave the infrastructure, the serving and building to Amazon as a managed service that allows us to, say, leverage, I think, what is a fairly small team compared with some others I've seen here, and deliver great results for our customers, which we can continue to build on. So thank you. I'll now hand back to Francisco to finish up.
Cool. Thank you, Amir, for sharing this great story with us. I think it shows clearly the advantages of implementing semantic search, as well as the strengths that lexical search brings. So I think it's important to keep both into the equation and think about them together, and not just explicitly go into lexical search because it has the ML part and all of that, right? I want you just to take some key takeaways here. I want to be nice with you. I know that you've been through a lot of sessions. If you just keep these two things as takeaways from this session, I would be happy. Just get a basic understanding of what vector search really is. you can identify vector search as a semantic search that is going to grab the semantic understanding of what you're trying to express, and it's going to work on the vector realm. So there's 2 steps needed in a vector search. You get the numerical representations, so you have to go from the text or the image, as Amir mentioned, or music into vectors or vector embeddings. This is the first step. And the second one is to find the similar vectors out of all the vectors that you have stored previously in your database. These 2 steps can be done by the use of Amazon OpenSearch Service, and there's 2 main plugins that you can use to implement these 2 steps. The first one, that is to get the numerical representation, can be done via the Neural plugin, and we saw the different options available to implement this. And the second one, that is the actual KNN search, can be done with the KNN plugin. Surrounding all of this, I would just want to iterate the crucial need to evaluate the search results and iterate, because building a search engine is not a plug-and-play thing to do. You need to iterate until you find the best results that you're looking for. These are some resources. Maybe you could go ahead and take a picture to it. I really encourage you to go to opensearch.org. It has great documentation, great examples, great blog posts with all the details of different implementations. And you can also stay connected via the social media platforms that OpenSearch has. Also, I want to reshare with you all the QR codes that we've been sharing throughout the session. These, in my opinion, are great sources of information to start your vector search journey, and I really encourage you to start and go into them if you are interested in this and learn more about it. Again, I want to thank you all for coming here, for choosing this session actually, and I hope you learned a bit more about vector search and the possibilities that you can achieve with this new technology. Have a great evening and enjoy the rest of the day. Thank you.